I'm glad you've chosen to learn a little bit more about power laws. It's important that if you're going to claim that your network has, say, a power law degree distribution, that it actually does. Because if it has a power law degree distribution with an exponent, between 2 and 3, this means that things are going to spread very effectively. They're going to be different strategies in immunizing the network, and the resilience of the network to node failure, as we'll learn in a little bit, is going to be affected as well. So we don't want to claim that our network is power law if it's really not. So let's see what power laws are about. Power laws are different from the normal distribution. The normal distribution looks something like this. You have the average height for a human male, and some are taller and some are shorter. And if you look at the max to min ratio, even looking at the Guinness Book of World Records, right, the tallest man is only several times taller than the shortest man. On the other hand, if you look at a city like New York City, it's 150 times 150,000 times larger than a small town of Duffield, Virginia. We've seen this before. This is the power law distribution on a log-log scale. Oh, sorry, this is it on a linear scale where we see like this very sharp L, and here it is on a log-log scale, and we see that straight line. That's going to be our signature. You see these distributions in many different domains. And here I should just say these are cumulative distributions. So rather than looking at the probability that, for example, in the first graph, that a word occurs exactly 200 times, we're going to be looking at the proportion of words that occur 200 times or fewer. And if your distribution is really power law, then this cumulative distribution, which is going to be its integral, is also power law, with its exponent being alpha minus 1. So if we see a power law in the cumulative distribution, we're actually seeing a power law distribution. And so you can see if you look at word frequency, that is, how many times in Moby Dick did the word whale occur versus the word the. Citations, how many citations did each scientific paper receive? Web hits, this is a data set that I analyzed back when I was a grad student. Books sold among bestsellers. Telephone calls received. Now, you might imagine that this is some sort of call center that received over 100,000 calls in a single day. Earthquakes, many, many small earthquakes, a few really large earthquakes. Yet more power laws, crater diameter, peak intensity of solar flares, casualties in wars, lots of small skirmishes, and then a few really large, very costly in terms of human life wars. Income distribution, a few very rich people and lots of not so rich people. Name frequency, lots and lots of Smiths and not that many, I don't know, lots of people have less common names. Populations of cities, we just talked about that. A few mega cities and many, many small towns. The power law distribution written out, we've seen this before, is that the probability of X, say a word occurring 100 times, is equal to some constant times X to the minus alpha, where alpha is typically between 2 and 3. And if we take the log of both sides, as if we were plotting on a log-log scale, we indeed see a linear relationship between the log of the probability of observing X and the log of the value X itself. We often hear power law networks referred to as being scale-free. What this means is that the power law looks the same no matter what scale we look at. So whether it's in the range of 2 to 50 or 200 to 5,000. And this is only true of a power law distribution, because if you change X by some multiplicative constant, that probability is just going to have another constant in front. You'll also hear power laws sometimes referred to as Ziff distributions. George Kingsley Ziff was a Harvard linguistics professor who first looked at the distribution of frequencies of different words in text. And some words are much more common than others. And there are all sorts of fun models trying to figure out why this is. One such model is that you're throwing down letters at random, but you include the space. And so the words are generated as just random letters and terminated by spaces. And that actually gets pretty close, but turns out to not be the correct model. But when Ziff was looking at, say, for example, distribution of words in text or the sizes of cities, another subject he studied, he termed it in terms of the size of the rth largest city. And so he got power laws with an exponent beta. And you can actually match the two exponents, because saying the rth largest city has n inhabitants means that our cities have n or more inhabitants, right? All the others are smaller. So this is in fact our cumulative distribution. And so you can flip things around and find that beta is actually equal to 1 over alpha minus 1. So if you have a power law distribution with an exponent alpha of 2, this is true of the number of unique visitors from AOL to websites. This is a very old data set, I think 1997 or so, that I studied as a grad student. When you plot the ranked plot, you're going to get an exponent beta of 1, exactly as you would expect. There's also a kind of an 80-20 rule. So using the exponent alpha, you can actually figure out whether it's 80-20 or 90-10 or whatever else. And this is just the amount of wealth that is in the hands of the richest P proportion of the population. And for example, for wealth distribution in the US, which is getting more and more skewed, the alpha exponent is 2.1, meaning that the richest 20% of the population holds about 86% of the wealth. Now let's get to the meat of the matter, which is how do you fit power law distributions? How do you know that the degree distribution that you measured on your network is actually power law? And what you start out with is this histogram. You know, I have this many nodes with degree 1, this many nodes with degree 2, blah, 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 right? And you may think, well, it's supposed to be a straight line on a log-log plot, so what I'm going to do is I'm going to plot it on a log-log plot, and I'm just going to try and fit a line to it. And this is problematic. Well, we'll see how it's problematic. Let's first see what it looks like on an artificially generated data set. So I just generated lots and lots of random variables, but I generated them in such a way that they're distributed according to an alpha exponent of 2.5. So we're going to know that a fitting method that gets close to 2.5 is actually a better one. So we're going to start with our little linear scale plot, and you see it already seems to zero out by the time it gets to 20. And over the whole range, we just see this L, which isn't very informative. And this is it on a log-log plot, and here actually it looks pretty good. It looks like we can plot this, but there's a basic problem, which is that here we have tens of thousands of observations, right? This is something like 100,000 of the data points that are generated were, you know, the number, I guess this might be 3, right? But then where we get into numbers that are over 1,000, right, there are many missing bins, right, because we just didn't get any number of, 2,373 or something like that. Maybe we didn't see that in this data set, and so we have a 0. which you can't take the log of, so it's just missing on this plot. And each of these points becomes an individual observation versus we have 100,000 data points going into here, meaning that we should be weighting this more, but we're not if we do a simple linear regression. And in fact, what you see happening is if you do a best regression fit, it's going to be totally misled by these points out here and the missing data that isn't represented, and you're going to get an alpha fitted exponent that's way too low, right? And so here it's actually saying, oh, the alpha may be something like 1.6, which it's not, right? We know that the data has came from a distribution with alpha equals 2.5. And this is just reiterating a few bins here, many bins here, but we actually have more data here than out here. So the first solution is to bin logarithmically. That is, you want to actually get more data here, so you're going to have wider and wider bins. And they're going to start 1, 2, 4, 8, 16, 32, or you can decide which exponent you want. And then you get these nice evenly spaced data points, which you can then fit. And if we do this, we get an alpha of 2.41, which is actually pretty decent. But what it's doing as well is it's kind of smoothing out the data and losing some information, right? When you aggregate into these bins, there may be interesting features that you're just kind of smoothing out and that you won't recognize. So the second solution is to do cumulative binning. Like all those plots I showed you with solar flares and family names and so on, those were cumulatively binned. There's no loss of information because each value captures, how many exactly do you observe, how many observations do you have of this value or lower? And so you don't have kind of zeros that are falling off or something like that. And so you can do just a regression and get this cumulative exponent, which is going to be alpha minus 1. So you'll have alpha. And that's also a fine way to do it. And here we get alpha minus 1 is 1.43, and that's much closer to the actual 2.5. So that's perfectly fine. There's also the question of where do you want to start fitting? Now, I drew from a pure power law distribution because I was generating fake data. But in reality, data isn't going to be so pure, so there may be some deviation on the lower end. For example, if you look at the number of links that different university websites get, each university gets at least a minimum number of links. So you're not going to get like the I guess from your point of view, lots of universities with only one link to their website. I mean, they wouldn't be a university if that was the case. So you may see something that's somewhat like this. So really, you just want to fit out here. You want to fit the power law there, but not be misled by the low values. So you can establish an x min, a minimum value, below which you're not going to be fitting. So if we look at, for example, citations, maybe the power law is only evident for papers that were cited at least 100 times. And so you can set x-min to be 100 and then fit the tail. There is the very, very best method, which is this max likelihood method that calculates using every one of your data points. What is, the observation that you have, the data points that you have, what is the most likely distribution? What exponent would it have that would have produced the data that you see? And if you want to use this kind of a method, you can download, and I'm going to provide the link separately, from Aaron Closet's site. And it's basically Python and R code that, you can use either one. You don't have to use both, even MATLAB code, I think. That given a data set, we'll first evaluate, is this a good candidate for a power law fit versus another kind of distribution such as the log normal or the stretch exponential, etc. And then if it is a good candidate for a power law fit, what is the power law? So if you're getting really serious about characterizing your network, I would recommend doing it properly. And this is the way it's done these days. So here's some exponents for real world data. You can see that most of them tend to be between 2 and 3, but some drop a little bit below 2. Now this is weird because these distributions would have, kind of infinite variance. So most likely they have a drop off. The power law can't extend indefinitely. So those were different data sets that weren't networks. Many real-world networks are power law. So if you look at film actors, this network is who has acted with whom in a movie. And there's a funny story around this, which is that the Sunbelt Conference, which is the annual social networking conference, had a data analysis challenge, which was to take the Internet Movie Database and plot out the network of all the actors, who has co-starred with whom, and calculate things such as who are the most central actors. And little did they realize that there's a certain kind of movie, namely pornography, that produced very high centrality actors because a single actor can kind of star in many, many movies, right? They're made at a very rapid pace, and so until the people participating in the challenge, met up at the Sunbelt Conference and started comparing notes. No one really expected that the porn industry would be so very central in the movie collaboration graph. Anyway. There's the telephone call graph, which we already talked about, right? Who calls whom? Email networks, sexual contact networks, which we talked about as well. The World Wide Web we talked about. The physical internet, also power laws, some very large hubs. Peer-to-peer networks, so for example, for file exchanges, some computers tend to be very central in these networks. And then different kinds of biological networks where you have either metabolites or proteins interacting with each other. But it's important to note that not everything is power law. So bird species abundance is not power law. Size of wildfires is not power law, even though some wildfires are very big and many are small. Even networks that appear power law at first, especially the social ones, for example, email. If you just take who has emailed whom ever, excuse me, you may get a power law, but once you start restricting that, like the other person actually replied, or maybe there was a little bit of back and forth, like some actual interaction, it ends up being not power law because people, there are really limits to how many relationships you can maintain, and so you lose the power law property. The electrical power grid, not power law. I guess the thesaurus, there isn't really a word that could be a synonym for every other word. The networks of company directors. So this is if you look at the boards of directors of different companies. So how many other people did you jointly sit on boards with? And even very hardworking, very prominent individuals only sit on so many boards, and so they only have a limited degree in such a network. So here's just an example on the AOL visitors data set. And if we try to fit it directly, we get an alpha that's way too low. If we do exponentially wider bins, we get a seemingly reasonable slope of 2.1. But it's real data. So if we do this kind of exponential binning, we may lose information about, there's actually a little bit a deviation from a power law where we don't have that as many sites as you would expect with very low numbers of visitors. And then again, in the tail, it doesn't quite match up to the power law. And so, what you may end up doing is fitting a power law with an exponential cutoff, which just says up to this value kappa, it's a nice power law, and then after that, it starts to decay exponentially. And there could just be different reasons for this. For example, constraints such as how many people you could ever interact with, or you can only there are only so many individuals available to connect to, etc. Right? There could be different reasons for these cutoffs. So just to wrap up, power laws are cool and intriguing, but you should make sure that your data is actually power law before you boast to others.